Welcome you all to this course on refrigeration and air conditioning. Today we'll discuss vapor compression refrigeration system, its basics and pH and TS representation of VCR cycle on the uh, pH and TS diagram, and then we'll see various performance parameters to evaluate vapor compression refrigeration cycle like COP, energy efficiency ratio EER, then IPLV, NPLV, integrated part load value, net part load value. So let us begin our discussion on vapor compression refrigeration cycle. So again, refrigeration as per ASHRAE, American Society of Heating, Air Conditioning and Refrigerating Engineers. Refrigeration is the science of providing and maintaining temperatures below the immediate surrounding temperatures, and this process of removing heat from the medium is the refrigeration in short. And the principle of refrigeration is based on second law of thermodynamics, the Clausius statement of second law of thermodynamics. And as we know that the statements Clausius second law of thermodynamic Clausius statement states that it is impossible to remove heat from the low temperature body and pump it to high temperature body without any work input. So that is a negative statement. So assertive sentence is like that: if you have to remove heat from low temperature body and if you have to pump heat from low temperature body to high temperature body, you need some work input. That work input is shown here. So this is the working principle of the refrigeration. Based on this refrigeration working principle, as you can see on this right hand side diagram, first A as a refrigerator, as you can see QL amount of heat, that is our desired output from refrigerator, is removed from a closed space, and with the help of some work input to the compressor. That's why W net, which is required as in the second law, stated in the second law of thermodynamics. And this because of that work, this QL amount of desired heat is removed from cold space, and it the QH is the amount of heat rejected to the surrounding. So this is the working principle of refrigerator, and same you can apply to heat pump. Only our objectives is now change. So QL amount of heat is removed from the surrounding, and with some work input, that QH is the desired output is given to your enclosed space. That is your desired output. So as you can see that you have to just reverse your objectives, otherwise the basic working cycle remains same for refrigerator as well as heat pump, and which is based on second law of thermodynamics. So this is the principle of refrigeration. So next, simple vapor compression refrigeration cycle. So this simple vapor compression refrigeration cycle comprises of four important components: evaporator, compressor, condenser, and pressure reducing valve or expansion valve, and so we can say. And uh, this cycle is divided into two parts. If you draw one center line, you can see that this cycle is divided into low pressure side and high pressure side. Clear? And so as we can see that this QO is the desired heat uh, that we have to remove from the space that we have to maintain uh, at the low temperature than the surrounding. So there our uh, target or our output is evaporator, where Q0 or QO is the amount of heat removed, and then that refrigerant, after absorbing heat from the evaporator, it gets vaporized or gets evaporated, and that vapor is then supplied to compressor. Clear? This vapor is then compresses in the vapor, and as you can see that that is goes to high pressure side, so its pressure and temperature increases, and that high temperature high pressure vapor supplies to condenser, where heat qk is the heat um, released or rejected in the surrounding, and then this uh, high pressure low temperature refrigerant is then passes to expansion valve, and expansion wall is nothing but the pressure reducing wall. So here you can see that this high pressure liquid from the which we obtain from the condenser is then converted into low pressure liquid. Okay, and this low pressure liquid then again supplies to evaporator, where after absorbing heat q0 it is get vaporizes, then compress, condensation, expansion, to cycle repeats. So this is the basic working cycle of vapor compression cycle. Based on this cycle, lots of devices nowadays we are actually using in day to day life, like refrigerator, heat pump, then chillers in very big central air conditioning plant, or domestic or office air conditioning. So everywhere you can see that most of the application today are based on this vapor compression refrigeration cycle. And then comes to next important point, that is unit of refrigeration. Whatever process we have discussed, there is some unit of the final output you are getting, and this is TR in refrigeration, that is tons of refrigeration effect we obtain. So capacity of this refrigeration is expressed in TR, that is tons of refrigeration. And this TR is defined as the quantity of heat removed in order to form 1 ton of ice at 0 degree Celsius in 24 hours from liquid water at 0 degree Celsius. So in short, you can say that it is nothing but quantity of heat to be removed from the water from and at 0 degree Celsius in order to convert it into ice in 0 degree Celsius in 24 hours, right? So after just doing some simple mathematical stuff, you will get 1 tr is equal to 12,600 kilojoule per hour, or if you convert it into minutes, then 210 kilo joule per minute, or in kilowatt it is 3.5 kilowatt. So 1 tr is nothing but 3.5 kilowatt. So as the definition explain, which is here, you can vice versa this, if you have to you can also say that it is the amount of heat to be rejected in order to convert the 1 ton of ice at 0 degree Celsius to liquid at 0 degree Celsius in 24 hours, that is 1 tr. And yes, I just equalizes that definition with this device 1 tr of AC in order to uh, makes you understand that is whenever you go to purchase any refrigerating or air conditioning device, its capacity expressed as tr. If you wish to purchase the air conditioner, you can say I need a 1 tr, 1.5 tr, 3 tr AC, 5 tr AC. Central chillers are up to hundreds of tr, 400 tr, 1400 tr, that kind of uh, capacity is expressed in TR. So I hope this unit of refrigeration you remember, and please do remember this correlation that 1 TR is equal to 3.5 kilowatt. Now next is refrigerator and heat pump. So based on this vapor compression cycle, these two devices that are widely used are, first is a domestic refrigerator that we are everybody is using in a house. And as you can see that this refrigerator is having equipped with four components that we have seen in basic simple vapor compression cycle, like evaporator, then compressor, condenser, and expansion valve. So our refrigerator in our house is again works on VCR cycle. Likewise for heat pump, as you can see that amount of heat is it as going to removed from the surrounding, plus the for that you need some work input, and finally this q is then supplied to the room. So this is working of heat pump and the domestic refrigerator based on vapor compression cycle. Now uh, the working fluid for this refrigeration cycle, as you can see that there is some working medium that needs to carry this heat, is nothing but the refrigerant. Okay, so based on the refrigerant that you are going to refer, you have to uh, uh, refer the properties of that refrigerant in order to evaluate and analyze the cycle. So uh, For that we are having first property table, refrigerant property tables, and these property tables are used to obtain various values of pressure, volume, enthalpy, entropy at different temperatures under saturated conditions. So as you can see that, for example, I have taken this refrigerant table for R134A refrigerant. As you can see that first column is of temperature, then saturated pressure corresponding to that temperature, then specific volume, internal energy, enthalpy, and entropy. So if you know any if you have to calculate the saturated properties from temperature, you can do that. Or if you know the pressure, then also you can you can find out, or the other, or you can calculate the other properties based on the with the help of this table. Clear? The thermodynamic properties of refrigerant under superheated, subcool, and two-phase condition cannot be obtained from this table. That is a limitation, because this table will give you only the saturated properties. Yeah, of course you can evaluate, or you can calculate the superheated, subcool, and all these things analytically also, but that is somewhat tedious thing. So in order to make it easy and quick for the field engineer, now lots for that we are using pH charts, that I will discuss in a while. So first, with the help of property table, you can evaluate the cycle. Then again come back to the vapor compression cycle and its representation on TS and pH diagram. So once again refer to our uh, basic vapor compression cycle. So basic vapor compression cycle comprises of evaporator, compressor, condenser, and expansion valve. So 1 to 2 compression, 2 to 3 condensation, 3 to 4 pressure reduction or the expansion process, and 4 to 1 is the evaporator, heat absorb in the evaporator. So same you can represent on TS diagram like this. So this is a saturated liquid line, saturated vapor line, the dome you can see. And on this TS diagram, as you can see, 1 to 2 compression. So 1 to 2 is compression, and that is a isentropic compression, right? And as we are representing a simple vapor compression cycle, or you can say a saturated vapor compression cycle, means entry to the compressor is the saturated vapor. So that's why my point 1 is on saturated vapor line. So I will plot this simple saturated vapor compression cycle, where point 1, that is entry to the compressor is, or the suction of the compressor is saturated vapor of the refrigerant. Then it is compresses isentropically. Then 2 to 3 is the heat removed, QH amount of heat removed in the condenser. So as we know that this condensation is a constant pressure process. So 2 to 3 is the constant pressure heat rejection in the condenser. Then 3 to 4 is the isenthalpic process, or expansion process, or throttling process. So 3 to 4 is the uh, isenthalpic process is shown like this, 3 to 4. And next, where you can see that pressure reduction takes place from high pressure to low pressure side. And 4 to 1 is the heat absorbed in the evaporator. So 4 to 1 is the heat absorbed in the evaporator as shown here, right? So this is a simple representation, or representation of simple vapor compression refrigeration cycle on TS diagram. Likewise, on pH diagram in refrigeration, we are going to uh, plot pH diagram, because this pH diagram will give you the quick value of enthalpy that we are going to, or that will help us to evaluate the cycle quickly. That's why pH diagrams are quite, or pH charts are popular in refrigeration, in order to evaluate the properties of the refrigerant as well as the performance of the VCR cycle, right? So as you can see that this pH on y-axis pressure and on x-axis enthalpy is written. And as again we'll start with point 1 on saturated vapor line. So dome is looks like this in on pH diagram, and point 1 is on saturated vapor line. So 1 to 2 isentropic compression shown here, 2 to 3 constant pressure heat rejection in the condenser, 3 to 4 is the expansion. So isenthalpic expansion, that's why H3 equal to H4. Enthalpy at 3 and 4 is constant, and 4 to 1 is the constant pressure heat absorption by the refrigerant in the evaporator, which is shown here 421. So this is the representation of VCR cycle on pH diagram, right? So this pH diagram will, as I had already told you, that this is a very helpful diagram in order to quickly obtain the thermodynamic properties of refrigerant as well as to evaluate the your VCR cycle. Then uh, this is one of the example of representation uh, it is the pH diagram for refrigerant R134A. So refrigerant R134A, this pH diagram is plotted like this: on y-axis pressure, on x-axis enthalpy, and this is a saturated liquid line, saturated vapor line, this is dome, and uh, the temperature lines are shown in blue, as you can see that -20, 0, 20, 40, 60, 80. So on blue is the temperature, saturated temperature lines. Then corresponding to these pressures given on the y-axis, and enthalpy is on the x-axis, and entropy is shown here in sky blue color, as you can see that 1.2, 1.1, 1.9 kilojoule per kg Kelvin. So these sky blue lines going with steep lines upward are the entropy lines. Then the dryness fraction lines are given in the dryness fraction, gives the dryness fraction 10, 20, 30, 40. So on this pH diagram, pressure, enthalpy, dryness fraction, temperature, entropy. So all these things are plotted on this pH diagram. So if you know any two properties out of these 5 6 properties, you are able to plot the you are able to fix the state of the refrigerant. Okay, and this will help you to evaluate the VCR cycle performance, that we'll see in a while. Now, analysis of VCR cycle. That VCR cycle we discussed at the beginning of this presentation is vapor compression refrigeration cycle. So in order to analyze this cycle, these 5 parameters are quite widely used in the industry, are COP, that is coefficient of performance, EER, that is energy efficiency ratio, then SEER, that is signal energy efficiency ratio. Fourth one is the IPLV, integrated part load value, and fifth one is the NPLV, net uh, part load value, that we'll see one by one. So lots of time these properties are uh, students get confused with COP, EER, IPLV and all that. So let us begin the discussion on these properties of vapor compression cycle, and we'll clear the things one by one. So first, COP. uh, the performance of refrigeration system or vapor compression system is expressed as COP, that is a coefficient of performance, and COP is nothing but the ratio of refrigerating effect or your desired output to the work input, that is the work of compression. So it is a ratio of refrigerating effect to the work of compression, and the cooling effect, that is the output of the system, is produced by the evaporator, and the refrigerant is compressed by using compressor, and the input to the compressor is the electrical power. So of course higher COP is always desirable, because higher COP is indicator of higher refrigerating effect and low compression work. So uh, as an refrigeration engineer, you always try to have to achieve more and more COP, means trying to getting more and more refrigerating effect. So COP is a very simple term used to analyze the vapor compression refrigeration system. Next parameter is energy efficiency ratio, which is in short called as a EER, and this energy efficiency ratio is nothing but the ratio of output cooling energy that you get divided by the input electrical energy. So output cooling energy we express in BTU, and input electrical energy is given in watt hour. So just remember that it is a ratio of your desired output, or that is a refrigerating effect in BTU, to the electrical energy in watt hour, right? So its unit is BTU, watt hour, and but most of the time the error or by mistakenly lots of people are calculating ER as a output cooling power in BTU per hour divided by electrical power in in watt, right? But as it is, as you, if you compare it with the actual definition, this is wrong. But the advantage is that it allows us to easily estimate the power use for certain size of air conditioning, and the value is not that much deviating. So lots of time this value is lots of people are mistakenly referring this ER as BTU per hour upon watt, but the actual definition is BTU per watt hour, right? So based on this energy efficiency ratio, various star rating, if you go to the market to purchase refrigerator, air conditioner, then this category 1 star, 2 star, 3 or 5 star refrigerators are available in the market. And as you can see that for every refrigerator, the categorization based on the star rating is given based on the its energy efficiency ratio. So as you can see that star rating of suppose 1 star refrigerator having minimum ER as a 3.1 and maximum 3.29, for 2 star 3.3 to 3.49, and for 5 star it is 4.5. So based on the energy efficiency ratio means of course higher output with less energy is given the 5 star rating. So the energy efficiency ratio is that's why having a very it's very significant in the industry when it comes to the performance analysis of the your refrigeration system. Then next to double ER, that is energy efficiency ratio, is the SEER, and this SEER is similar to that of ER. The only difference is the seasonal thing, and this seasonal energy efficiency ratio represents a measurement of how the system behaves over the season. Means it will not uh, take throughout the season, because if you take the energy efficiency ratio throughout the year, it will not take into account the seasonal variation. So the seasonal variation throughout the year is taken into account by this SEER, and that's why this SEER term is coined and used nowadays, because it will give you the value or the performance of your refrigeration system over a season. Clear? So that's why the uh, definition of SEER, that is seasonal energy efficiency ratio, is the output cooling energy in BTU over a season divided by input electrical energy in watt hour during the same season. So output in BTU upon watt hour, the definition remains same. The only difference is over the season. The seasonal variations are taken into account. That is a SEER. Then for Indian context, this SEER is slightly modified as ISEER, that is the Indian Seasonal Energy Efficiency Ratio. So for Indian point of view, in India, if you're a manufacturer, then you have to specify the ISEER for your refrigerator or any other HVAC device, because this is ISEER represents the actual amount of heat removed by your system to the energy consumed during the process in the over the season, right? So the only change is that this IEESER is in on Indian context, the values of seasonal variations are taken into account. Then next most important term is integrated part load value, which is in short called as IPLV, and simultaneously we'll see this non-standard part load value, that is NPLV, and this NPLV is again similar to the IPLV. So let us see what is the difference and what is the integrated part load value and non-standard part load value. So IPLV or NPLV is used to evaluate the efficiency of the chillers at different loading condition, and to calculate the calculation formula for IPLV and NPLV is nearly same. The only difference in integrated part load value and non-standard part load value is, I think, the name nomenclature itself is self-explanatory, that IPLV is the integrated part load value and non-standard. Okay, so NPLV is a non-standard. So IPLV is based on the standard as per the AHRI standard 550-590. Clear? So AHRI is the Air Conditioning, Heating and Refrigeration Institute, and this AHRI will uh, standard 550 590 is given for this IPLV standardization. If you're evaluating your refrigerating device with respect to the standard, then the value obtained is called as the IPLV. Clear? And if you're not following this standard 550 590 and you are evaluating the part load value or the performance of your chiller based on the site condition or your the local conditions, then it is called as a non-standard part load value. So IPLV and NPLVs are uh, the formula remains same, but the only difference is the condition uh, based on which you are going to uh, doing the trial or test your device. So why IPLV and NPLV is calculated, right? Because we are already having COP and EER to evaluate the performance of refrigeration system. Then why IPLV and NPLV? So I COP and EER are calculated based on the full load capacity. Suppose I am using 1 TR refrigerator, so that the assumption is that when I am going to calculate COP, I will assume that the refrigerator is fully loaded. Clear? But in real world, in day-to-day life, or chillers, particularly air conditioning devices, are never or hardly they run on their full capacity. Most of the time, they are partly loaded. So the value you obtain from COP and EER and the actual performance is different, right? So for that, this term uh, IPLV or NPLV was coined in order to take into account this part load performance of your system. Chillers, in this case I'm referring chiller, that is again which chiller is supplied chilled water or for clear. So these chillers are the refrigeration system in short. So this refrigeration system has one of the example of Chilltrix CX 34 air conditioner is given, and when they surveyed and they found that most of the time your refrigerator or sorry your chiller is at 75% capacity, runs at 75% of their full capacity or 50% of the capacity. So 50 more than 80% of the time the chiller works between 50 on 50 to 75% of the load, full load. Clear? And then 25 12% on 25% capacity, and only you can see that interestingly their chiller works 100% at their 100% capacity only 1% of the time. Clear? It shows that the COP and EER values calculated are of no use because they are based on the assumption that on which your refrigerator or chiller works only 1%. Okay, so most of the time your HVAC devices or refrigeration devices are works on part load performance. That's why this in IPLV or NPLV is calculated, and they will take into account the part load performance of the refrigerating devices. So they have calculated the values performance of these refrigerating devices are measured at different loading conditions, say 100, 75, 50, and 25%. So calculation, how to calculate IPLV and NPLV. So IPLV and NPLV is for as I told you that they are calculated for part load performance. Part load energy efficiency is calculated at 70, 100%, 75, 50, and 25%. So various load points, these four load points are fixed, and the values of COP at these 4 points, that is, for example, A is COP or EER at 100%, B is at 75%, C is 50, and D is 25%. So with the help of the formula, so IPLV or NPLV is given as 0.01A, 0.42B plus 0.45C plus 0.12D. So this is the formula to calculate IPLV. But if you don't have COP or EER, and instead of this, if you have to use this kilowatt per TR tons of refrigeration, then you simply inverse the things, that is IPLV or NPLV is nothing but 1 upon 0.01 by A plus 0.42 by B plus 0.45 by C plus 0.12 by D. Only inverse and slight modification in the formula is required when you are uh, using the units, okay, A, B, C, D as kilowatt per tons instead of COP or EER. Then the slight modification in the formula, but this is the simple formula to evaluate the performance of your refrigerator based on the this formula. Clear? And this part load performance at IPLV and NPLV, as I already told you, that it is calculated based on the AHRI standard 550, 590, and this 550, 590 standard for various chillers, that is evaporator, base that water cool condenser, air cool condenser, evaporatively cool condenser. So based on the types, IPLV is standards and non-IPLV is non-standards. Of course, no standard mention in the IPLV is followed in calculating the NPLV. The detailed standard you can obtain from AHRI website, where you will see the detailed procedure of how to conduct the IPLV test with this standard 550, 590. One of the case study of IPLV and NPLV calculated on Chilltrix chiller and CX34 model. As you can see that the part load performance at various loading 100, 75, 50, 25%. They have calculated the capacity, total power, energy efficiency ratio, COP, and finally EER, IPLV based on EER, and second is a part load performance for NPLV. So NPLV or EER is given. So IPLV is 23.02 as they have find out, and NPLV is comes as approximately 31 only, right? So this is such type of data you will get purchasing, or the manufacturer will provide you the product catalog where the IPLV and NPL values are mentioned. Now let us see one example on based on the vapor compression, simple vapor compression refrigeration cycle, to evaluate the performance of that cycle, right? And finally we'll find out COP of that cycle. So in the given example, as you can see that the condition, various condition across the various components like compressor, condenser, expansion valve and evaporators are given, particularly pressure and temperature is given, and with the help of this we have to find out heat absorbed by the evaporator, means Q absorb in the Q evap, so heat rejected in the condenser Q con, and work done to drive the compressor, that is W comp, and finally COP of the system as either refrigerator or heat pump. We'll calculate both COP as a refrigerator and COP as a heat pump. So let us begin this analysis of this VCR cycle given in the example, and we'll calculate these various parameters as mentioned here. So VCR cycle, first of all plot this given condition on PS diagram. So so I have plotted this point 1, 2, 3, 4 with the help of pressure and temperature given in the example on the pH diagram like this. So first is temperature is given as -20 and it is written as it is saturated vapor, right? So saturated vapor means it will be on saturated vapor line. So saturated vapor line is this, and temperature is given as -20. So -20 and saturated vapor line, it is plotted like this point 1, right? Then this after suction it is get compressed, and after compression condition of the refrigerant R134A is pressure 1 megapascal and temperature 70 degrees Celsius. So uh, 70 degree so temperature lines are given in the blue, so 70 is between 60 and 80. Okay, here you can plot the line like this, and pressure is given at megapascal 1, so megapascal 1 megapascal line and this 70 degree Celsius line intersect here, and which is given as point 2. Point 3 is after condensation pressure remains same, it is a constant pressure heat rejection, okay, and temperature is given as 30. So 30 degrees Celsius is again between 20 and 40. So they, here you can plot like this, and your 1 megapascal line intersect here. So this is your point 3. Point 3 to 4 is the throttling, adiabatic throttling, and here enthalpy remains constant, means H3 equal to H4. So enthalpy is on x-axis, so H3 equal to H4. You can plot a vertical line, and after 4 to 1, okay, 4 to 1, the pressure and temperatures are given, where you can plot point 4. Okay, the intersection of 3 to 4 on with this evaporator pressure line gives you the point 4. So point 1 2 3 4 are plotted on pH diagram like this. Now I have to evaluate the uh, heat or work interaction across each component in vapor compression cycle. So first let us begin with the compressor. So 1 to 2 is the compression, where pressure temperature is given and you have plotted 1 to 2 line like this. This is the isentropic compression, as we already discussed. So as it is open system, you can or steady flow, you can apply the steady flow energy equation to this compressor, and we know that steady flow energy equation is given as Q minus W equal to delta H plus delta K plus delta P. So for the isentropic compression, uh, Q is 0, kinetic energy, potential energy negligible, so W is equal to delta H, and delta H is H2 minus H1. So enthalpy at point 2 and enthalpy at point 1 is, you can find out by extending this 1 and 2 on the x-axis. You will get the values of H1 and H2. So after subtraction, you will get the compression work at 65.5 kilojoule per kg. The minus sign indicates work is done on the system. Okay, so work of compression is 65.5 for the given example. And here you can also okay, find out the next condenser enthalpy across enthalpy exchange across the condenser. Again apply steady flow energy equation to the process 2 to 3, that is the constant pressure heat rejected in the condenser. Then of course Q is there, no work involved, so W0, Kep is negligible, so Q is equal to delta H. And after finding the values of H3 and H2 from this pH diagram, you can uh, find out the total heat rejected in the condenser like this. So in the given example, it is minus 210, which is minus sign indicates again heat is rejected. Then value of enthalpy for across the expansion wall. So we know that throttling process is a constant enthalpy process, isenthalpic process. Or if you don't know, again write down the steady flow energy equation, and Q0, W0, Kep negligible, so delta H is 0, means H3 equal to H4. That you can directly find out by extending this 3 to 4 line on x-axis, and you'll get the value of enthalpy, that is 93.6 in this case. So H3 and H2 H4 you find out. And finally across the evaporator, that is 4 to 1. So 4 to 1 steady flow energy equation, Q is there, W0, Kep negligible, so Q is equal to delta H, and H1 and H2 you already know. And finally we'll find out Q evaporator is 145 positive, because it is absorbed by the, or heat is supplied to the refrigerant. Okay, that's why it is positive. So after substituting the values into the formula of COP, so COP of refrigerator is given by your desired effect. So desired effect, where you will obtain the desired effect in the vapor compression cycle, is in the evaporator, right? So heat absorbed in the evaporator is Q evap, that we already calculated, divided by compression work input. So work input is given to the compressor, so W input is compression work we already calculated. So COP of the refrigerator comes to be 2.2. Clear? Same, if you, if this is the heat pump, not a refrigerator, then formula is total heat rejected to your cabin is Q, is of course your objectives will change. In refrigerator, evaporator is your desired uh, device where you'll get your desired effect, but in heat pump your objective changes to condenser. So Q condenser is your desired output in heat pump, and work input is again in the compressor. If you put substitute the values, you will get the COP of heat pump as 3.2. Clear? As you can see that the same cycle, if you work as a refrigerator, the COP is 2.2. If the VCR cycle, same cycle works as a heat pump, then you will get COP as 3.2. So from this you can notice that for the same system, COP of heat pump is always greater than COP of refrigerator by 1. Clear? So you can from this you can draw a conclusion that COP of heat pump is equal to COP of refrigerator plus 1. Okay, so with this you can plot the vapor compression cycle on pH diagram, and with the help of pH diagram you can find out the, or you can analyze the vapor compression refrigeration cycle like this. Okay, thank you all for your attention. In the next lecture or in the next session we'll see the multi compression refrigeration system. Till then, bye bye and stay tuned.